Already, we are continuing with our study of exponential functions in section 5.5. The start thinking part says determine if each of the following represent exponential growth or decay. Next, determine what the original amount is and the percent growth or decay. So on here, it's important for you guys to understand the basics. You want to think through problems, don't try to memorize things. For example, you should know that if you multiply by a number larger than 1, the original number gets bigger. If you multiply by a number smaller than 1, down to 0, obviously not 0, but if you start approaching 0, it is going to be getting smaller and smaller and smaller. So that's going to be able to tell you whether it's growth or decay. So the first one, you are multiplying by a number greater than 1, 1.24, so it's going to be growth. Next one is being multiplied by a number smaller than 1, 0.72, that's decay. And the last one is being multiplied by a number smaller than 1, so that's decay as well. The next is figuring out what the original is. Now, we know what the formula looks like. Y equals a times 1 plus r to the x, or 1 minus r to the x. So the a is always going to be original. So you can see that it's 30 and then 1.56, and then by default, the number in front is a 1 on C. But another way you can do this is just the fact that the original is at time equals 0, or when x equals 0. So when you substitute in 0 for any one of these exponents, anything to the 0 power equals 1. So the first one, you would get 1.24 to the 0 power, which is 1, and 1 times 30 is 30. Explains two different ways to show the original is 30. Same thing with B. 0.72 to the 0 is 1, and 1 times 1.56 is going to be 1.56. And then the last one, when you substitute in a 0, anything to the 0 power equals 1. So the original is 1. Now, what you need to really understand is we're just trying to figure out how far away from 100% or 1 we are getting. So on the first one, it says 1.24, which is 124%. 100% of that is just getting the original number back. So this is really only going up by 24%. That's why it's 24% growth. The next one, like I said, if I go to Vegas with $1,000 and leave with $1,000, I have 100% of my money, even though I did not gain anything. So if you had 100% normally and now you're down to 72%, then that must have been dropping by 28%. And then the last one, you normally have 100% of your money. This is 6.2%. So you have dropped down by 93.8%. And this should make sense because if you multiply any number by 0.062, you're going to barely have anything left. So if you wanted to call that 6.2% decay, you're going down by much more than 6.2%. Now, the next thing we studied here was just looking at a real-world example of exponential decay. So it says, in order to control an algae bloom in a lake, scientists introduce some treatment products. Once the treatment begins, the area covered by algae A in square yards is given by the equation A equals 240 times 1/3 to the x. They needed to figure out what the 240 was and what the 1/3 is. The 240 is pretty easy because we know what the equation looks like. That's going to be your original amount. Now, the confusing part here is always that other number. People never know, is 1/3 going to be how much it's going down by or what you have left? Let's say you didn't know how to do this. You could take any number. Let's say you take 100 and you multiply it by 1/3. You end up with 33.3 repeating. Now, you can ask yourself, did that mean that only a third went away? Or does that mean I only have a third left? And that means that you only have a third left, which should make sense that that is actually a reduction of 2/3 each week. So the 1/3 actually tells you that it went down by 2/3 and you have 1/3 left for every week that this is going on. Then what we did was we substituted in 0, 1, 2, 3, and 4 into our equation. And a lot of times I jump and make the equation, well, they already gave us the equation of 240 times 1/3 to the t, and we just substitute in the 0, 1, 2, 3, and 4, and you can get your different values of the output. And when you graph those, you see that nice, pretty curve, which is your exponential decay curve. There are two different questions I asked the students. I said, between which 2 weeks is the percent decrease the most? And it's a trick question because the percent decrease is always exactly the same. It's always going to be 66.6% decrease or 2/3 decrease. Every time it's always that same percent. Then when you ask when was the most square yard decrease, that is between 0 and 1 week, because that is going to be 2/3 of the largest possible number, which is 240 square yards. The bottom, which I do not believe actually showed up on the notes for the students, says about how many square yards of algae will there be at 2.5 weeks. We can either substitute that into our equation, or we can just look at the graph. You get a much more accurate answer if you substitute into the equation. The next thing we did was we looked at this. This is, as I told you, there are many things that are modeled by exponential decay. One of them is half-life of medicine in your body, or just how the body is metabolized the medicine is metabolized by your body. So this says a patient who is diabetic receives 100 micrograms of insulin. The graph shows the amount of insulin in micrograms remaining in his bloodstream over time in minutes. So it says scientists have found that the insulin in the patient's body changes exponentially. How can you check if the graph supports this? So first off, we just check. Make sure it's not like a line or something that doesn't look like exponential growth or decay. And it does have that nice curve, so I feel like it's in the running for exponential decay. The next part says how much of the insulin broke down after the first minute. What fraction of the original is that? So it was a change of 10 micrograms, and the original was 100, so that meant it went down by 10%. Also means that there is 90% left. And the way I did that was I said the new number is 90, the old number is 100, so that means the new number is 90% of the old one, aka 10% decrease. On C, it says how much broke down after the second minute. So 9 went down over 90 minutes. Sorry, 9 went down, and the amount right before that was 90 micrograms, and that is a 10% decrease. So that goes along with the previous one that was 10% as well. The other thing was we went from 81, and the one right before was 90. So I found out that 81 was actually 90% of the previous, meaning there was 90% left, aka a 10% decrease. So, and when you check the next one as well, that also turns out to be a 10% decrease, meaning 72.9 is 90% of 81. And so it is looking like it is going to be exponential. What fraction of insulin remains in the bloodstream for each minute that passes? Explain your reasoning. So it's 90%, and I'm going to explain the reason. The reason was I just found out how much was in there and how much that was of the previous. So 90 was still there out of the 100 that was there before, and that's how I got my 90%. And you can do that for all the rest of them. The next one says fill out the table. Even though we don't have an equation yet, I made the equation because that makes it much easier for me to figure out what the remaining numbers are. So we have the original and then 1 minus the 10%, which is 0.1 all to the x. And when you substitute in your values for the number of minutes, you end up getting 65.61 and 59.049. You also could have just taken that number and multiplied by 0.9 every time, because every time there should be 90% of the insulin left in the body. And then lastly, it says, what is the generic equation, which we have here? And lastly, how much will there be after 10 minutes? So we're able to substitute 10 in for the exponent, and you get 34.9 micrograms. All right, for the homework, you guys really need to be able to differentiate between linear growth and exponential growth. Linear growth, there's always going to be a common ratio, meaning a common difference. For linear means that you're either adding or subtracting the same number over and over and over, which gives you a constant slope. And exponential is going to be a common ratio. Sorry if that was confusing. I was just accidentally reading it in the order that I saw these problems. So the first one we see, are you adding or subtracting the same number over and over as long as the numbers on the left are consecutive, which they are. And you are first adding 10, then 20, then 40. So that is not adding the same number. You are not having a common difference. Are you multiplying by the same number over and over? And yes, you are multiplying by 2 over and over. You could also look at 20 over 10 is 2, 40 over 20 is 2, 80 over 40 is 2. So you could look at the ratio of those, common ratio. The next one is the landfill. This is going to be linear because it is a common difference. It is increasing by the same exact amount every single day. It's going to be increasing by 2 tons per day. And if you graph this, you would see that it was a nice straight line with a constant rate of change, a constant slope. Now, the next one is talking about migrating butterflies. They started out with, it looks like via the equation, 100,000, and then you have that factor, which is less than 1, which tells you that it is decreasing. W is going to be the number of weeks. It wants you to complete the table. So we can substitute in our values and get our values for the population. See those? Went over and graphed. I saw that there were 10 tick marks, and I needed to get up to 100,000, so I just went by 10,000s. Now, one thing that I did wrong here, please make sure that you label your graph. So that is definitely a mistake on my part, but I'm not going to re-record the video. It is just going to be, you need to have the left saying the population of butterflies and the bottom saying the number of weeks. So don't forget those. I will fix the key, which I post though. All right, so you see how I graphed that. I went by ones down on the number of weeks, and I was able to get my graph. It says, what is the vertical intercept? What does this tell you about the butterfly population? So it is 0, 100,000, meaning there was originally 100,000 butterflies. Next one about when does the butterfly population reach 50,000? So first I looked at the graph to figure out what numbers I could start popping into my calculator. And it looks like 50,000 is a little bit after 3. So I just started testing out numbers like 3.4, too big, 3.3, still too big. And I found out it was right around 3. It was like 3.08 or something like that. I was just testing it out. When you guys get to Algebra 2, you'll learn how to solve this backwards, where you solve for the exponent. You have to use something called logs. Okay, on number 3, it says find the coordinates. Since this is exponential, whatever the percent that is dropping by will be a consistent percent that you'll be taking away. So you can see it is dropping by 200, which is a 20% decrease. So what you can do here is just go over and continually take off 20%, meaning you continually are going to have 80% remaining. So when you do this, you could say 80% of 800 gets you 640, 80% of 640 gives you 512, and then 80% of 512 gets you 409.6. Once again, that is because there is a 20% decay, 80% left over. On number 4, the graph shows the amount of chemicals in the water sample at different times after it was measured. Select all statements that are true. The first one says the amount of chemicals in the water sample is decreasing exponentially. And while it looks like it's actually decreasing exponentially, the issue here is we're not able to calculate the exact decrease for each one of those, so we can't test it perfectly to make sure that it is decreasing at the right rate. The next one says that it is not decreasing exponentially, and at first when I read those, I was like, it has to either be decreasing exponentially or not. What I didn't do is read C, and C says it is not possible to tell for certain whether it is decreasing exponentially. So that is the actual answer. It might be depending on what those exact values are. So C is one of them. D, when it was first measured, there were 2,000 milligrams of chemical in the water sample. And you can see that at time equals 0, it is going to be 2,000. And lastly, after 4 hours, there were 100 milligrams. If you look at 4 hours, that looks like a bit more than 1/4 of the way. Looks like 1/3 of the way up to 400. So that's not it either. Next, go ahead and drag it down so you can actually see it. Hang on, sorry. There we go. Okay, the last one says the graph shows the amount of chemical in a patient's body at different times in hours since the levels were first checked. Could the amount of chemicals in the patient's body be decaying exponentially? Explain how you know this. So when we look at this, I can see originally it dropped by 40%, which means you have 60% left. And then when you check what is 60% of 600, you do get 360. And since both of them end up being 60% of the previous, meaning a drop of 40%, that is going to be possible that is exponentially decaying. So it says decreases by the same percent amount after each period. All right, thanks for watching.